This is John Whitaker for the Probability 1 class, and this is going to be our 11th video lecture. And last time, we computed a CDF in a discrete case, given the joint PMFs. And now I want to calculate the joint CDF in a continuous case, and we'll do an example of that. And it's a lengthy example, and it uses the joint PDF that we've seen before. So here, if the joint PDF of x and y is f of x comma y equal to, now let's write that here. It's a piecewise defined function to be that 5/16 xy squared if 0 is less than x is less than y is less than 2, and 0 otherwise. Our question is to find the joint CDF of x and y. And in terms of the solution, here's what I'll start off with. We'll note that if, and again, note the CDF, let's start off that way, the joint CDF. Is denoted by f of a comma b. Okay. Well, because of the definition of the joint PDF, what we notice is if, so this is case 1, if A is less than 0 or B is less than 0, then the joint CDF will be equal to 0. So that's the first case that we have. Okay, now let's look at case 2, where if we look at the A values representing about x, is less than or equal to 0, but is less than 2. Okay? And the reason I'm picking that type of range is because of the way that the PDF is defined, the joint PDF is defined. Don't forget, the joint PDF is 0 everywhere except for here. Okay? So, look, what we're saying, if A is less than 0 and B or B is less than 0, then we already know that the joint CDF is going to be 0. So we've got to find here. Now I'm just saying, well, what if this is an A somewhere in here? Then how are we going to define the F of AB, the CDF? Well, we're going to break it up into subcases. So the first subcase is 0 is less than or equal to B is less than A. So in this subcase, then f of AB will be equal to, it'll be the integral, because of the definition of the CDF, from 0 to B. Okay. So here, it's as if I'm looking at this type of region. Okay? And so here, I'd only have to be integrating over this spot. So what I have is the x values, I'm sorry, the y values run from 0 to b, but the x values would run from 0 to y, and then we have the PDF, which is f of 5/16, I should say, xy squared dx dy. Okay, so when we do this integral, this is the integral from 0 to b. Here I'm integrating with respect to x, so this is going to be 5 over 32 x squared y squared. I'm going to evaluate when x goes from 0 to x equals to y. And here, when I do that, that's going to be equal to, so I stick in x equal to y. This is going to be the integral from 0 to b of 5 over 32 y to the 4th, and when we let x be 0, we just get 0, so dy. This is going to be equal to, it's going to be the antiderivative here is going to be y to the 5th over 5, so it's going to cancel with the 5 in the numerator. So it's y to the 5th over 32, 0 to b is what y can range from. So this is b to the 5th over 32. That's what we get for this type of situation. The next part, for the next region in the xy plane for which we're going to find these joint CDF, is in the subcase where b is going to be bigger than or equal to a, but yet less than 2. Then, here's what we have. The joint CDF is going to be equal to, and I'm going to change the order of integration. And so in this case, it's going to be from 0 to a. Okay, then it's going to be from x to b of 5/16 xy squared dy dx. I'll change the order of integration of this part. And when we look at this, that's going to be, I'm integrating with respect to y, so it's going to be 5, and from 0 to a, 5 over, this is going to be y cubed over 3, so that's going to make this 48. X, y to the 3rd, y is being evaluated from x to b, and then dx. That's going to be equal to the integral from 0 to a of 5 over 48. Here, remember I'm sticking in values for y. It's going to be b to the 3rd x minus, and then it's going to be x to the 4th. So 5 over 48 x to the 4th. dx. And then that's going to be equal to, so it's going to be 5 over 96 b to the 3rd x squared minus, it's going to be x to the 5th over 5. That's going to cancel with the 5 in the top, so I'm going to have x to the 5th over 48. I need to stick in 0 and a for x. So what I end up getting here is 5 over 96 b cubed a squared minus, this is going to be a to the 5th over 48 in this subcase. All right. For the last subcase in this category, we're going to have the situation where b is bigger than or equal to 2. And so in this case, f of ab is going to be equal to, again, I'm going to do the integration dy dx. So x is run from 0 to a, and then the y values will run from x up to 2, that's all we'll have to integrate over, of the joint PDF, so 5 over 16 is xy squared, and here we're doing dy, then dx. Okay. And so this is going to be the integral from 0 to a. We're integrating with respect to y, so this is going to be 5 over 48 y to the 3rd x, and we need to evaluate that as x goes from, y goes from x, I should say, to dy dx. And that's going to be equal to, okay, so I stick in 2 for y, that's 8. So it's an interval from 0 to 8. When I have y cubed, that's 8. That's going to be 5, 6 then, because 8 over 48 gives me the 1 over 6. So it's 5, 6, x, and minus, when I let y be equal to x, I'm going to have 5 48ths. This will be x to the 4th. I need to integrate with respect to x. That's going to equal, so this is 5 12 x squared minus, it'd be x to the 5th over 48. And that's evaluated from 0 to a. And that's equal to 5 12 a squared minus a to the 5th over 48. And that's the last subcase we have where a is between 0 and 2. And so now we look at the case 3, if you will, where a is bigger than or equal to 2. We're going to have two subcases here. So subcase 1 is going to be that b is between 0 and 2. And in this case here, that's going to be, again, the interval from 0 to b, that's what the y's run from. And the x values will run from 0 to y here, 5 16ths x y squared dx dy. That's what we have. And that's based on the definition of the CDF, the joint CDF, and using our particular joint PDF here for where it's non-zero. That's what we have. And that's exactly part of the problem we get done earlier. And what we get for that, it's the same calculation that we had earlier in the subcase. So we're going to get for that. I'll redo it, but this is equal to, okay, we're integrating with respect to x. So here I'm going to get interval from 0 to a. And then here this is going to be 5 32nds x squared, y squared. The x values run from 0 to y. And then whatever I get for that, I have dx. That's equal to 0 to a, 5 32nds. This is going to be y to the 4th, minus 0. So, I'm sorry, this should have been dy. I made a mistake in my writing over here to the left. Let me go ahead and correct it. Okay. So look here at the bottom board. I got dx, that's wrong. It's dx, dy. Okay, so make that correction. Then what we're having over here is correct. Okay. Sorry about that. dy. This is going to be y to the 5th over 5 as an antiderivative, so it's going to be 1, or y to the 5th over 32, 0 to a, and that ends up being, I'm sorry, it shouldn't be 0 to a. It says 0 to b. There's a mistake here. Gosh. This is b, and that ends up being b to the 5th over 32. That's the way I have the subcase. And then subcase 2, what we have here is if b is bigger than or equal to 2. Okay. In this case, what we're going to be integrating is we're going to be integrating from 0 to 2, integral from 0 to 2 for the x's, of the 5 16th x y squared dx dy. And this is something we've already calculated as 1. Okay. And so we can summarize now what the CDF, the joint CDF is for this particular problem. So f of AB is equal to, so it's this huge piecewise defined function. And it's 0 if a is less than 0 or b is less than 0. It's b to the 5th over 32 if 0 is less than or equal to a is less than 2 and 0 is less than and in this case if 0 is less than or equal to b is less than a. And then here we had 5 over 96 times b to the 3rd a squared minus a to the 5th over 48. And that was what we had if we had 0 is less than or equal to a is less than 2 and a is less than or equal to b is less than 2. Then we have 5 12ths a squared minus a to the 5th over 48. And that was if these two things are happening. That is 0 is less than or equal to a is less than 2 and b is greater than or equal to 2. Then we had b to the 5th over 32 again. And that was if a is greater than or equal to 2 and 0 is less than or equal to b is less than 2. And then we had 1 if a is greater than 2 and b is greater than or equal to 2. That's what we could summarize it. It's a complicated, long calculation. I want to look at a fact about the joint CDFs, much like we had a fact about the joint PDFs or PMFs, and that recovering the individual CDF from the joint. And so here, if f of AB is the joint CDF of x and y, then the first thing we have is that this should say, I think that, yes, f of a infinity is equal to f sub x of a, which is the CDF of x, and 2, f of infinity b is equal to f sub y of b, which is the CDF of y. And let's prove that. So here's the proof. It's very simple. They're very similar, but they're so simple to do both of them. Here, let's note that if you look at the CDF of x, okay, that's equal to the probability that x is less than or equal to a, which is the same thing as the probability that x is less than or equal to a and y is anything. So here, if you will, y is less than infinity. And so that is nothing more than f of a infinity for the joint CDFs. And 2, the second part, again, it's the very same proof. F sub y of b is equal to the probability that y is less than or equal to b, which is equal to the probability that x is less than infinity and y is less than or equal to b, and that's nothing more than f of symbolically infinity b. So that's the proof. Another fact, if x and y are jointly continuous random variables, then if you have the partial derivatives here with a and then b of FAB, that's going to be equal to, that's the partial derivatives for the CDF, that's going to be equal to the joint PDF of x and y. Okay? And so here's the proof. So here, if you take the partial derivatives here with respect to AB of f of AB, what this means is we're going to take the partial derivative with respect to B first of the joint CDF. Okay. And that's going to be equal to, here, this is writing the partials that need to be done. What this is the double integral. So here is the double integral from minus infinity to b, the way we define it, minus infinity to a, of f of x comma y dx dy. And what I'm going to do is I'm going to switch the order of integration. No, I'm sorry. What I'm going to do is move in this partial, I'm going to switch the order of integration. That is right, I'm sorry. So this is a partial with respect to a times part and then, not times, doing the partial with respect to b. And here, switching the order of integration, this is going to be minus infinity to a, minus infinity to b of f of x comma y. Here I'm going to have dy dx. Okay, and then that's going to be equal to moving the derivative inside, one of the partials inside the integral. So here from minus infinity to a, now I'm going to take this partial derivative and here this is f of x comma y dy dx. Okay. Look, we look at this integral. That's nothing more than previous fact. It's going to be the derivative with respect to b here of this quantity and this integral. And so that is nothing more than the partial derivative with respect to a minus infinity to a, and here this is going to be f of x comma b dx And then this derivative now is going to be f of a comma b, where we're using the fundamental theorem of calculus where the one variable is being held fixed. Okay? So that's what we have. That concludes the proof. Definition I want to talk about next is an expected value for a function of x and y. If g is a function of random variables x and y, then the expected value of g of x, y is denoted by expected value of g of x comma y, and it's going to be given by so here the expected value of g of x comma y, okay, it's equal to the sum over the x value, sum over the y values of, here it's going to be g of little x comma y, f of x comma y, okay, when x, y are discrete, and f of x comma y is the joint PMF, and then it's equal to 4 is the integral from minus infinity to infinity, minus infinity to infinity of g of x comma y, f of x comma y dx dy when x and y are continuous, where f x comma y is the joint PDF of x and y. I'd like to do two examples where we're using this definition. One discrete, one continuous. So in particular, we'll look back at any f we've used before. So we'll let f of x comma y equal to x plus y over 21, where x could be equal to 1, 2, and y could be equal to 1, 2, or 3. Then, so what we're going to find is the expected value of x squared y. This is g of xy, it's x squared y. Okay, what it's going to be equal to is the sum over the x values, which is 1, 2, sum over the y values, which are 1 to 3, of x squared y, and then we have to multiply that by the joint PMF, which is x plus y over 21. Okay, so when x is equal to 1, let's see what we have. We have 1 squared, and then we're going to let y run from 1 to 3. So when y is 1, we have 1. And then here, it's going to be 1 plus 1, so that's 2 over 21. Again, we're still holding x being equal to 1, so I have plus. Now y is going to be 2 this time, so it's 1 squared plus, times 2, times, here's 1 plus 2, so it's 3 over 21. Plus, again, x is still 1, y is 3 here, so it's 1 squared times 3, and then this last part is 4 over 21. Plus, now when x is 2, we're going to have 4, so 2 squared times 1, and then this is going to be 2 plus 1 over 21, that's 3 over 21. Plus, this again is going to be 4. Y is 2 in this case, so 2, and here we're going to have 2 plus 2, that's 4 over 21. And then here we're going to have, again, x is 2, so 2 squared is 4, and then y is 3, and then this is 5 over 21. Okay. So when we add these together, we're going to get here, this is it's 2 over 21, plus this looks like 6 over 21, plus this is going to be 12 over 21. This is going to be another 12 over 21. This is going to be 32 over 21. And here this is going to be 12. It's going to be 60 over 21. And 60, 92, 94, 104, 106, 116, 122, 124 over 121. That's what we got. Not over 121, but just 21. Okay. And so that's a example in the discrete case. For a continuous example, let's look back at that familiar joint PDF. So here we'll let f of x comma y be equal to that 5/16 xy squared if here we have not much room here. Let me back it up. So let f of x comma y be equal to 5/16 xy squared if 0 is less than x is less than y is less than 2, and 0 otherwise. See that? Okay. Good. And then the expected value of x squared times y in this case is going to be equal to this double integral, minus infinity to infinity, minus infinity to infinity of g of x comma y, f of x comma y, dx dy. Okay. Now, f of x comma y a lot of times is 0, so we end up having to integrate. You'll remember, I think I have room to drop right here. We have, the y values run from 0 to, the x values run from 0 to, we have this y equal to x. So we want y to be bigger than x, that's this region. So here this becomes an integral. The y values run from 0 to 2, and for each fixed y value, the x value will run from 0 to y. And here I'm going to have x squared y, and then f of x is 5/16 xy squared, and then dx dy. Simplifying this, we get 0 to 2, the integral from 0 to 2, the integral from 0 to y. 5/16, here's going to be x to the third, y to the third, dx dy. This is going to be equal to, so I do the integration with respect to x. It's going to be an integral from 0 to 2, so here it's going to be 5. With respect to x, I'm going to get x to the 4th over 4. The 4 and the 16 is going to make 64 at the bottom. And here this is x to the 4th y to the third. We're going to let the x values run from 0 to y. And then once we get an answer, we're going to have dy. I think I have enough room here to write down 0 to 2 is the interval that we're going to have, 5 over 64. And then when x is equal to y, we get y to the 7th. And when x is 0, we get nothing, so that's dy. Okay, and so completing that integral, we have this is going to be equal to 5 over 64 y to the 8 over 8, evaluate from 0 to 2. Okay, now look, the way I think about this, this is 5. I stick in 2. When I stick in 0, I'm getting nothing. So it's 5 over 64. And then when I have y to the 8, and I'm going to stick in y equal to 2. Really, that's going to be 2 to the third times 2 to the fifth. Okay, and that's over 8. But the 2 to the third is 8, so that's going to cancel that. So we're left with 5 64 times 2 to the fifth. Well, 2 to the fifth, 2, 4, 8, 16, 32. So here, 32 and 64 leaves a 2 in the bottom. So we get 5 halves, and that's the answer for that. Now, as a fact, because of this definition of how we take the expected value of a function of x and y, what we have as a fact is that the expected value of the quantity x plus y is equal to the expected value of x plus the expected value of y. Now, I'm going to do this a little bit different than the way than the way that's presented in our text. Okay? So here, I'm going to have case 1, x and y are discrete. And so the expected value of x plus y is equal to the sum over all x values, sum over all y values of x plus y. Here, this is going to be f of x plus y. I'm sorry, f of x comma y. And what we're going to do is we're going to distribute that function f of x comma y. We're going to do that first, and then we're going to break it up into two different sums, two different double sums. Addition, two different sums. Okay. So this is going to be equal to sum over the x values, sum over the y values of x, f of x comma y, plus y, f of x comma y. Now, the two double sums, this is x, f of x comma y, plus the double sum of y, f of x comma y. Okay, here I can take the x out, because it's a constant with respect to y. And in this interval, I'm going to switch the order of the summation, and we can do this. Okay, but I'm not going over y. It can be done in these cases. So here's y. We can, looking at the next line, here when you sum up over all y, the joint, what you get, if sum over y, is you get the PMF of x. Plus, here I'm going to factor out a y because it's constant with respect to x. Here, when you sum up over all the x values x times its PMF, what you get is the expected value of x. And here, this is plus, this is the sum over all y values of y, and here is the PMF of y, which is expected value of x plus the expected value of y. And that's what we wanted to get in this case. The continuous case works pretty much the same. I'm going to do it. But instead of having summations, we're going to have integrals. Okay. So case 2. If x and y are continuous, then the expected value of x plus y is equal to minus infinity to infinity, minus infinity to infinity. Here this will be x plus y, f of x comma y, dx dy. And it's the same proof, okay? Minus infinity to infinity, minus infinity to infinity. Same proof as what we did before in terms of procedures. It's x, f of x comma y, dx dy, so we'll skip a step, plus the double integral of y, f of x comma y, dx dy. This is going to be equal to, here I'm going to switch the order of integration, minus infinity to infinity, minus infinity to infinity, x, f of x comma y, dy dx, plus, I forgot the integral, excuse me. So here, this is the inner integrals with respect to x, so the y is a constant, so I'm going to pull it out. Here, now, this is x is a constant, so I can pull it out. You can't always switch the order of integration in general, but you can in these cases, but I'm not going over why. So here, this is x, this is minus infinity to infinity of f of x comma y, dy dx, plus, here this is the integral from minus infinity to infinity, this is y. Here, this inner integral is the integral from minus infinity to infinity of f of x comma y dx. That's nothing more than f sub y of y dy. This is equal to integral from minus infinity to infinity x. This is second integral, the inner integral here is f sub x of x dx. Plus, if you look at the single integral here, this is the expected value of y. And if we go back and look at this first integral here, that's the expected value of x. And so in all possible cases, we get the expected value of x plus y is equal to the expected value of x plus the expected value of y. And so that's the proof. The next topic I want to hit upon is that of independent random variables. So I'm going to give a definition here. So random variables x and y are said to be independent if for any two sets A and B that are subsets of R, the probability that x is in A and y is in B is equal to the probability x is in A, comma, y is in B, and y is in B. I'm sorry, times the probability that y is in B. Okay, that's what it means to be independent. I think you can see it. Okay, and then an alternative definition. I'm not going to show these definitions are equivalent, but x and y are independent. Okay, if f of AB is equal to f of x of A times f of y of B. So the joint CDF is equal to the product of each individual CDF. Okay. Let us get up a fact about another way of thinking of independence. So, as a fact, x and y are independent if and only if f of x comma y, so that's the joint PDF, PMF, is equal to the products of each individual PMF, PDF for x and y. So it's an if and only if statement. So we're going to have two directions. So here we're going to let x and y be independent. Okay, we want to show that this relationship between the PDF or PMFs happen. And so here, case one is if x and y are discrete. So then, in this case, if you look at f of x comma y, what that's going to equal to is the probability that x is equal to x and y is equal to little y. And that can be thought of as the probability that x is an element of the singleton x and y is an element of the singleton y. And by our first definition for independence, that's the probability that x is an element of the singleton x, little x here, times the probability that y is an element of the singleton y, which is equal to the probability that x equals to little x times the probability that y equals to little y, and that's equal to f, the probability mass function of x times the probability mass function of y. So in case one, we have the result we were looking for. So for case two, we're going to have x and y are continuous. Okay. And then what I'm going to have, we're assuming that x and y are independent. So let me write that. Since x and y are independent, then what we have is the joint CDF is equal to the products of each individual CDF. Okay? And so, if you take these derivatives, okay, so what this is going to be equal to, that's going to be equal to little f of AB, which we've already shown. Okay, and if you take the partial to be f, the other side, f of x a times f of y b. Okay. So if you look at this, that's going to be equal to the partial with respect to a, and then acting on the partial with respect to b of f of x a times f y b. And that's going to be equal to, so here, when you do it with respect to b, this quantity is a constant, and so you just write it down. But here, this partial of this guy is nothing more than its derivative, which is little f sub y of b. And then here, this quantity is a constant with respect to a, and so we're just writing it down. And the derivative with respect to a big F, is nothing more than little f. Okay. And so what we have is what we've shown is, so the derivative of these derivatives of the joint, okay, is equal to f of AB, but that derivative of the joint is the same thing as the derivatives of the multiplication of each individual CDF because of independence here. And that answer that we got is here. So this guy is equal to this guy, so that means this guy is equal to this guy. And that's what we wanted to show in this case. And now we still have a direction in the opposite. We still have the proof in the opposite direction because if and only is taken. Not much longer. So here, we suppose, going backwards, that f of x comma y is equal to f sub x times f sub y of y. We want to show x and y are independent. Okay, so case 1, x and y are discrete. And so here's what I want you to notice. If you look at their joint CDF, that's the sum over the x values less than or equal to a, sum over the y values less than or equal to b of f of x comma y. Okay? But that's equal to the same sum of f sub x times f sub y of y because of independence. And then you can take out the f sub x sub x. And here's the sum of the y's b of f sub y of b. And that's nothing more than, here this would be sum over the x values. But this second sum is nothing more than f sub y of b. Okay? Doesn't depend on A, you can take it out, so you just have this sum. And that sum is f sub x of A. Okay, so we've proven what we want in this case. And that is that the joint is equal to the product of each individual. So that says x and y are independent. One of the definitions for independence. And we only got one more case. Okay. So this last case, our x and y are continuous. And so here, I'll use the other definition for independence. So probability x is element of A, y is element of B. To show independence, I need to show that the probability of x is in A times probability of y is in B. Well, by definition, what this is a double integral. Which equals to, here, this is going to be B, A, here's f of f sub x of x times f sub y of y, okay. Dx dy, right, dx dy, and that's equal to, so the f sub y's can be taken out because it doesn't have an x in it. Integral of A, f sub x, dx dy. This inner integral is nothing more than the probability that x is in A. That's going to be a constant dy, so it can be pulled out. And then we have an integral over b of f sub y of y dy, which is the probability, that second integral is the probability that y is in B. And that's what we want to show. The probability of x is in A and y is in B is equal to the probability of x in A times the probability of y in B. So x and y are independent. Okay, ladies and gentlemen, that's enough for this lecture. I went over time. Thank you very much for your time and patience.